during the first cycle, the value of the capacitance has reached to its maximum value, which is 100 volt, equal to the source voltage Vs. What happens is, during the negative half cycle, when the supply is cut off, the source Vs is cut off from the circuit due to the reverse biasing of the diode. This capacitor will now supply to the load, and the capacitor will discharge from its peak value 100 volt to 80 volt, from this value to here. Now when once again the new cycle comes, the value of the diode is in forward bias now, and the capacitor will again charge from its value 80 volt to peak value 100 volt. Now you see that the capacitor is charging during this time period, and this is the time period during which the diode is operating. And this time period has been labeled as T nu. So you can see that previously the time period T old was large. We had a greater time period T, this time period T old, and the value of the current was low. It was because we had a large amount of time during which a small number of charges were being deposited on the capacitor or towards the load. But now when large value of the capacitor is applied, the conduction time of this diode has reduced to be T nu. Now that the time period has reduced, which means that, let's say that this is the new time period T nu shown here. So in order to supply the same amount of the current, this peak has to increase. Which is shown here. Why the peak has increased? Because now the time period, the conduction time of diode has reduced, and the number of charges to be deposited per unit time has to increase in order to maintain the same value of the current. So that's why the peak value and the surge value of the capacitances and of the diode will keep on increasing. So this is what I have tried to write down here, that the conduction time of diode has decreased, which is equal to T nu, which means that the charges to be deposited on the capacitor have less time now, or obviously from capacitor these charges will move towards the load. So now they have less time, due to which the charges per unit time will increase. That's why the current peak will increase. So the first thing in the design was to consider its ratings, its peak, surge and other values. Then we came towards its selection of the output filter, and how the value of the output capacitance filter affects the different peak, surges, peak and other values of the diode to be selected for particular application. And now the third one is input filter. It is an optional, we may or we may not want to use it depending on our requirement. So there is another thing I wanted to discuss related to this surge current, is that it might be possible that you have gone through different calculations or designing and you have considered all the values, RMS value, peak value, average value and peak inverse value of diode. But most people, what they do is they tend to ignore this I surge. You can see that although even if you have considered all these values, the surge value of the current, it is very large as compared to the RMS value or the average value of the circuit. So it is necessary that you take this factor into consideration as well, and whenever designing, make sure that your diode does not get damaged from this very first surge that will come. Okay, so now again there are some terminologies moving towards the performance parameters. We have defined a few performance parameters on the basis of which we can judge the superiority of a rectifier, or how do we even decide which rectifier topology will be better and which one not. So we have defined some performance parameters. Let's see what are those. So first of all, a few descriptions of the different terminologies. We know that the DC value is the average value. So the output value, output DC power will be equal to the average value of voltage multiplied by average value of current, that is VDC and IDC. Now similarly, PAC output power, AC power output has been defined as VRMS into IRMS. So now coming towards the very first parameter on the basis of which we can define the performance of our design, or the correctness or the superiority of our design, it is efficiency. Efficiency is defined as the ratio of DC power to the AC power, which means that whatever AC power has been applied from the input side must be completely converted into the DC power. That is, there are no issues of losses, and there are no harmonics in our system, and all the power that is being delivered is real power, and there are no harmonics, no reactive power, and nothing else. So in a perfect case scenario, this efficiency can be 100%. Ideal case scenario, this efficiency can be 100%, which means that the AC power supplied has been completely converted into DC without any ripples in its output waveform and any loss in our diode or any other part of the circuit. Now the effective RMS value of the AC component in the output voltage is defined as VAC. VAC is equal to square root of VRMS square minus VDC square. So we know that in the output voltage that we will obtain should be like this, complete perfect DC. But if we zoom it in a little bit, or the filtering is not very good, we will see that there are some ripples overriding over this DC signal, which means that there are some AC content in our output signal. So that is defined as VAC is equal to VRMS square minus VDC square root. Now the next parameter on the basis of which we can judge our performance is form factor. Form factor is defined as VRMS divided by VDC. The form factor is a measure of shape of the output voltage. That is how perfect our output waveform is. Then the another performance parameter is ripple factor, RF, and it is the measure of ripple content in our output signal. So it will be equal to VAC by VDC. Now there has been now we have introduced an alternative form for ripple factor. Ripple factor is equal to